In the last video, we explored evals, structured tests that help us measure and improve the behavior of agentic AI systems. But evals only work if we have good visibility into what the agent actually did. And that's where observability comes in. Observability is the layer that captures everything happening inside an agentic workflow: the traces, logs, model inputs and outputs, tool calls, timing information, and metadata. This is the raw material that makes evaluation possible. Without observability, you can't see where an error began, why a tool was chosen, or how the model's reasoning unfolded across a long chain of steps. With it, you can inspect real interactions, identify recurring patterns, and feed those insights directly into evals and continuous improvement. So you can think of observability and evals as working together. Observability collects the evidence. Evals turn that evidence into structured measurement and feedback. In this video, we will unpack what observability means in practice, how it enables debugging and improvement of agentic systems, and how the emerging tool ecosystem supports modern AI pipelines. Before we look at tools or workflows, let's clarify what observability actually means in the context of agentic AI systems. In traditional software, observability is about logs, metrics, and traces. Enough information to understand what a system did and why. For agentic AI systems, the idea is similar, but the data we need is much richer and more complex. Here, observability means capturing model inputs and outputs, every message, prompt, and response, tool calls, what was called, with what parameters and why, intermediate reasoning steps, chain of thought summaries, or decision traces when available. Retrieval events, what documents or data were retrieved. Timing and latency information, where the workflow slows down. Metadata, user context, model versions, environment details. All of this forms a trace, a detailed timeline of what the agent did from start to finish. Why does this matter? Because agentic systems are non-deterministic, multi-step, and often opaque. Without observability, you're effectively blind. You see only the final answer, not the path that produced it. With observability, you can debug behavior, detect failure patterns, improve prompts, tune retrieval, and most importantly, generate the high-quality evidence needed for evals. Now that we know what observability captures, the important question becomes, what can we actually do with all this information? Modern observability gives us several powerful capabilities that are essential for building and improving agentic AI systems. The first one is debugging real interactions. You can inspect individual traces to see exactly where an agent misunderstood a user, made the wrong tool call, or hallucinated. This replaces guesswork with concrete evidence. The next one is identifying systematic issues. By looking across many traces, observability helps you spot recurring failure patterns such as bad prompt behavior, misfired tools, or unreliable retrieval. The next one is supporting evals and error analysis. Observability provides the raw data for eval workflows. You can pull real examples, categorize failure modes, and build eval datasets directly from traces. And the next one is monitoring performance over time. As your system evolves, observability lets you track drift, detect regressions, and verify whether model or prompt changes actually improve things. And the last one is understanding agent reasoning. With structured logs of chain of thought surrogates, tool sequences, and intermediate outputs, you gain insight into how the agent approaches different tasks. In short, observability is not just about logging. It is what makes debugging, evaluation, monitoring, and improvement possible in agentic AI systems. To make observability practical, we rely on specialized tools that capture traces, visualize agent behavior, and help us debug and improve our systems. Several platforms have emerged that focus specifically on LLM and agent workflows. They all provide variations of the same core capabilities: logging prompts and responses, tracking tool calls, visualizing traces, labeling errors, and integrating evals. Some of the most commonly used tools today include Langsmith, a platform offering detailed tracing, dataset and prompt management, versioning, debugging tools, and integrated eval workflows. LangFuse, an open source observability and analytics platform for LLM applications, offering tracing, scoring, prompt management, experiment tracking, and dashboards. Phoenix from Arise AI, an open source observability tool focused on trace visualization, embeddings, drift detection, clustering, and deep inspection of LLM behavior. And BrainTrust, a platform specialized in evaluation workflows, including structural eval, pipelines, data set management, and analysis of model outputs. Another couple are weights and biases, or W&B. This provides LLM tracing, logging, and artifact tracking as part of the broader weights and biases ML experiment platform. And last but not least, OpenAI logs. Lightweight built-in logging through the OpenAI platform for capturing prompts, outputs, timings, and metadata. Each tool has its own strengths, but they all give developers a way to inspect real interactions, track errors, and create the feedback loops needed for reliable agent behavior. Now that we have seen some of the major observability tools in the ecosystem, it's useful to understand the types of capabilities they actually provide. Most observability platforms for agentic AI systems fall into a few common categories. First, trace and log capture. These tools automatically record model inputs and outputs, tool calls, intermediate steps, metadata, and timing information. Everything you need to understand what happened inside an agent workflow. Second, visualization and trace inspection. Platforms provide timeline views, tree-style traces, or graph structure so you can explore exactly how an agent reached a decision and where errors originated. Third, evaluation and quality assurance support. Many tools integrate directly with evals, allowing you to attach matrix, run automated checks, or connect an LLM as judge to score results on real traffic. Fourth, monitoring and alerting. They can track degradation over time, identify drift in model behavior, monitor latency and tool usage patterns, and notify you when something breaks. And finally, dataset and prompt management. Some platforms offer ways to version prompts, store datasets, label outputs, and build feedback loops that connect real traces back into your eval pipeline. By grouping tools into these capability areas, it becomes much easier to choose the right platform, whether you need deep debugging, large-scale monitoring, or integrated evaluation workflows. To understand how observability actually works inside an agentic AI system, it helps to break it into three essential stages. First, the system needs trace capture, recording every prompt, model output, tool call, and intermediate step that occurs during interaction. This creates the complete picture of what the agent actually did. Second, these traces are enriched with metadata such as model version, scenario labels, user identifiers, and experiment flags. This additional context makes it possible to analyze patterns, filter by conditions, or compare runs over time. Finally, the enriched traces are sent to an observability platform where they can be inspected, searched, compared, rerun, and evaluated or linked to eval results. These three components, capture, enrichment, and send, form the core of any observability pipeline and make continuous improvement possible. Most of this workflow becomes available automatically simply by integrating an observability platform's SDK. In this video, we explored how observability forms the foundation for evaluating and improving agentic AI systems. We saw that traces, metadata, and logs provide the raw evidence of what an agent actually did, making issues visible and measurable. We briefly looked at the growing ecosystem of observability platforms. We also broke observability into three essential stages: capturing traces, enriching them with context, and sending them to the observability platform. Together, observability and evals create a feedback loop that enables systematic debugging, performance monitoring, and continuous improvement for agentic systems.